A short one, and today will be about the construction of pseudorandom objects. So why do we look at these things? So what have we seen so far? We already saw that we can construct eavesdropping secure symmetric encryption schemes from pseudorandom generators. Basically the one-time pad where we replace the truly random string by a string that was generated using such a pseudorandom generator. Then we also saw that we can construct CPA secure encryption schemes from pseudorandom functions. This was very important construction where we kind of hide the randomness that we use or modify the randomness that we use using the pseudorandom function, but also include the randomness itself. And then we constructed secure message authentication codes, again, from pseudorandom functions. Basically, we saw that a pseudorandom function is a good message authentication code, although, as we saw, it has these length restrictions that are not so nice, so that's why we use also other ways or we use other techniques to circumvent these problems. And then we used the CPA secure encryption schemes and message authentication code to construct authenticated encryption schemes. And given these two results, we only need pseudorandom functions to construct authenticated encryption schemes. And then once we constructed these authenticated encryption schemes, we saw that we can construct CCA secure symmetric encryption schemes from pseudorandom functions because we saw that authenticated encryption schemes are CCA secure. And since we can define those from pseudorandom functions, we can also define CCA secure encryption schemes from pseudorandom functions. And these are the ultimate goal in the area of symmetric encryption schemes, namely CCA secure. So given pseudorandom functions, we can provide authenticity and we can provide confidentiality in the way we would like it to provide, namely with CCA security. So that obviously raises the questions, how can we construct pseudorandom functions? Where do we get them from? Because all this is based on the existence of pseudorandom functions, or in the first case, pseudorandom generators. And that is actually what I will discuss briefly today. So the goal is, how can we, since I said at the beginning of the course that we want to construct secure cryptographic primitives from general assumptions. So then now in this area of symmetric cryptography, this all boils down to the goal of constructing pseudorandom generators and pseudorandom functions from general assumptions. And the assumption that one needs to construct these things, but that are also necessary, is the existence of one-way functions or one-way permutations. This is a potentially stronger assumption that one-way permutations exist. One-way functions, the existence of one-way functions is enough for the construction of pseudorandom functions. And the outline, and I won't go into the details, if you're interested in the details, go into the lecture notes. There I provided the proofs in detail, but using one-way permutations because that makes the first step much easier. And the steps that we take is, we assume that one-way functions or one-way permutations exist, then we can construct one-way functions with so-called hardcore predicates. Hardcore predicates are predicates of a value of an x that are hard to predict given only the function value of x. Okay? So you're not given x itself, but the hardcore predicate is defined of x. Instead, you're given f of x. And then given f of x, it's hard to predict or compute this other predicate. And one can show that if one-way functions exist, hardcore predicates exist. And then one can show that hardcore predicates and one-way functions or one-way permutations immediately lead to pseudorandom generators with expansion n+1. So we can expand our truly random bit string by 1 bit. That is then indistinguishable from a bit string of length, a truly random bit string of length n plus 1. That obviously is not good enough for our constructions of symmetric encryption schemes, but what we can show is that once we have PRGs with expansion n plus 1, we almost immediately get PRGs with polynomial expansion, with arbitrary polynomial expansion. So once we have one-way functions, we have one-way functions with hardcore predicates, we get PRGs with expansion n plus 1, and then we get PRGs with polynomial expansion. And once we have PRGs with polynomial expansion, in fact, PRGs with expansion to n suffice, we can construct pseudo-random functions. So pseudo-random functions are not harder to construct than pseudo-random generators. That's somewhat surprising because they seem to be much more powerful, but we can show that from pseudo-random generators we can construct pseudo-random functions. The other direction is immediate. Once you have a pseudo-random function, you have a pseudo-random generator. Okay, so that's not such a big deal. Okay, so these 4 steps then show that the existence of one-way functions or one-way permutations is sufficient to construct message authentication codes, secure message authentication codes, and to construct CPA or CCA, secure symmetric encryption schemes. So the question obviously is, what are one-way functions? And why do we believe that they exist? We cannot prove that they do exist because that would at least imply that P is not equal to NP. In fact, it probably is a little bit harder. Okay, so what are one-way functions? So one-way functions, the name one-way comes from one-way streets. In a one-way street, you are allowed to go one way, you are not allowed to go the other way. In a one-way function, it's easy to go one way, and it's very hard to go the other way. That's why they are called one-way functions. And it means that the direction that's easy to go, it's easy to evaluate the function. The hard direction is inverting a function. So given a function value, you have to find a pre-image. And to formalize this hardness of the reverse direction, the inverting direction, we obviously, as we always do in this course, we use a game, the so-called function inverting game. Okay? And so this is about defining one-way functions, and we do that with this inverting game. So let f from 0, 1 star to 0, 1 star be a function. Let me stress that in one-way functions, we do not necessarily require that f is injective or even bijective. So this is an arbitrary function. And the inverting game now is, I give you a function value for which I know and guarantee that it does have a pre-image. You have to find some pre-image. You don't necessarily have to find the one that I, as you will see, that I use to construct the image, but you have to find one pre-image. There may be many, but the way the game is defined, you are always guaranteed that there is a pre-image. So in addition to this function f, we have also a PPT A, the adversary, and the inverting game for f and a is then defined as follows. On input n, so this is the so-called the security parameter, but in this case it has a slightly different meaning. So we pick an element x uniformly at random from 0, 1 to the n. Okay? So that is the meaning of n. This specifies the domain from which we pick x uniformly at random. We cannot pick x uniformly at random from 0, 1 star because that is infinitely large, and we cannot pick uniformly at random from infinitely large domains. And then we set y to be f of x. Okay? So y is the image of x. x. But given y, you know that there is a pre-image. A pre-image of y, there is an x such that f of x is y. Then a gets its input 1 to the n, and y, and eventually, after its internal computation, it outputs an x prime. And the result of the game is 1 if and only if f of x prime is equal to y. So if x prime is a pre-image for y. It need not necessarily be this x, because that would be unfair. I mean, there could be many x's that map to y. And how should you, as an adversary, just knowing y, how should you know which one was picked? Right? So you have to compute one pre-image, but not necessarily the original one that was used in step 1. So, and then we write invert a, f of n is 1 if the output is 1. And in this case, we say that a has won or succeeded. So the goal of the game from the adversary's point of view is to compute a pre-image of this y for which we know that there is a pre-image. Again, let me stress, f need not be injective or biject or surjective. So if I just pick some y, then there is no guarantee that this has a pre-image, but because of step 1, I know that it has a pre-image. And then we say that the function f from 0 is 1 star to 0, 1 star is called a strong one-way function. The strong is in brackets because if I say one-way function, always means strong, but there's an alternative definition that I give in a minute. So the function f is called a strong one-way function if, first, there is a probabilistic polynomial time algorithm f of f, such that for all x in 0, 1 star, if I start m and f on input x, it produces the function value f of x. So we can evaluate f efficiently. That's the first step. Note that since mf is required to be a probabilistic polynomial time algorithm, we know that the length of f of x is always polynomially bounded in the length of x. Right? Because the polynomial time algorithm, m gets as input x, so its input length is the length of x. It cannot produce an output as a probabilistic polynomial time algorithm that's polynomially longer than the input. Because just writing down the output would require too much time. So this is the easy direction. There is a probabilistic polynomial time algorithm that evaluates the function efficiently. That's easy. The hard direction is that for all probabilistic polynomial time adversaries A, there is a negligible function mu, such that for all n in n, the probability that A wins the inverting game against f with n is bounded by this function mu of n, by this value mu of n. So no efficient algorithm can win the inverting game except with negligible probability. So that's the hard direction. So if you go to that Goldwein's book, actually on the cover, you see that here is x, here is f of x, and then here is easy, and here is hard. That's one way. But notice that we do not require in the inverting game again that algorithm reproduces this x. It just has to reproduce one pre-image, not necessarily the one used in the first step of the inverting game. So that's called a one-way function. Okay. And alternative notation that you'll see often is that, and that makes it even clearer that we do not require the adversary to recompute the original x, is for a y in 0, 1 star, we set f to the minus y as the set of all pre-images. So it consists of all x in 0, 1 star such that f of x is y. And then we can write this probability here also as the probability that the inverted A wins the inverting game against F, as the probability that A on input f of x, then we denote by A of f of x, the output of A on input f of x, that this output lies in f to the -1 of f of x. Which means that, so this is our y, so it just has to produce one element from this set, not necessarily the original. So that often turns out to be a very useful notation. If you study Oded Goldreich's book, you will see that he loves this notation and pushes it much farther, so that he has a really very nice and concise way of describing probabilities and success probabilities. But it gets a little bit, and that takes some time getting used to. So this is an alternative way. You have to produce an element from the pre-image set. Okay. So this here is a very strong requirement. If you go back, this says that if you go to this game here, even for random images, or for random elements and the corresponding images, you can almost never, as an adversary, recover the pre-image. For random, call this a random image, this way, constructed in this way. For random image, you can always never construct a pre-image. Okay? That seems to be very strong, because there may be images for which it can be very easy to construct pre-images. There may be even many images for which it's hard to construct, for which it is easy to construct pre-images. And we want to have, and if you think about it, this seems like a very strong requirement, and that makes it maybe a little bit harder to believe that these things exist. In fact, all candidates that we have at the very beginning, the original candidates, do not have this property, but they do satisfy a weaker property from which we construct objects that have the stronger property. And those things are called weak one-way functions. And let me define what a weak one-way function is. So first of all, we will never deviate from this requirement here. This is always what we need. And then we call a function a weak one-way function if there is an integer c larger than 0, such that for all probabilistic polynomial time adversaries and all n, it holds that if we again pick x uniformly at random from this, A gets as input f of x, the probability that it's not in the pre-image set is 1 over n to the c. So this means that for random images, the probability that it does not succeed is significant, is non-negligible. These things are not this is not the opposite of this. This here is, well, that it's, this here means that the strong one-way function means that the probability over the x from 0, 1 to the n invert, let me write it with the other notation. So the probability that A of f of x is not in f to the minus f of x is larger than 1 minus mu of n, or it's 1 minus mu of n. Okay? So this here means that it's almost 1 not to produce a correct preimage. Whereas this here means it's bounded away from 0 by this function 1 over n to the c, which is very different. Bounded away from 0 by this 1 over n to the c is not being really, really close to 1. So these are really different definitions and different requirements. And this here seems to be like the more realistic requirement. This here says it's almost always hard to find preimages. It's almost always hard. This says there are some hard cases. It's not always easy to do so. So that is sort of the two things that we have. And not being hard doesn't necessarily mean being very easy. Could be also something in between. Now, the interesting thing is, so this is a comparison. The interesting theorem is here that one-way functions, weak one-way functions exist if and only if strong one-way functions exist. Which does not, this theorem does not say that weak one-way functions are strong one-way functions. It says that given a weak one-way function, you can construct a strong one-way function. Okay. And the way you do that is, I'll explain this in a second, because it requires a little bit of convention to do that, how you do that. But so once we have weak one-way functions, we also have strong functions. So our assumption usually is the existence of weak one-way functions. Then from those we construct strong one-way functions, and those are required for our constructions of hardcore predicates, theorem generators, theorem functions. Let me also briefly define one-way permutations, which are in the lecture notes. I explain how to use one-way permutations to construct PRGs and PRFs, not one-way functions, because there is one step in there that makes life much harder. And so here is a definition of one-way function. And first we need the definition of what is a length-preserving function. We had a similar definition when we talked about pseudo-random functions. So let again be f function from 0, 1 star to 0, 1 star. And f is called length-preserving if for all x in 0, 1 star, it holds that the length of f of x is equal to the length of x. So length always measured in number of bits. So f goes from 0, 1 for all n. If I give you an element of 0, 1 to the end, then the image is also in 0, 1 to the end. And we denote by f subscript n the restriction of n to domain 0, 1. And then we say that f is a one-way permutation if, first of all, f is length preserving. For all these restrictions, f is a bijection, and f is a strong one-way function. So permutation doesn't just mean that this function from 0, 1 star to 0, 1 star is a permutation. But for all n, the restriction must be a permutation. So it's a permit. As you can easily see, it's a one way. These two things are satisfied if f is length preserving and it's a bijection, because then this here is immediate. Okay, so we want this from all 0, 1 to the end. It just permutes the elements, and we also want it to be a one-way function. Permutation is a function, so we can obviously apply our previous definition. Okay, and let me just briefly go back to the original thing here. This step here, going from one-way functions to PRGs with expansion n+1, it's relatively easy if you work with one-way permutations. If you work with one-way functions, it becomes a 60-page proof. Here, it's a one-page proof. So permutations preserve randomness much better than functions. That's basically the reason behind it. Okay. So this is the definition of one-way permutations. Now, what do we know about the relation between one-way functions and one-way permutations? It's unfortunately not known whether the existence of one-way functions implies the existence of one-way permutations. We do think that both types of objects exist, but it's not known how to construct from a one-way function a one-way permutation. If one-way permutations exist, obviously one-way functions exist because they are functions, but the other direction is not known. So it could be the case that one-way functions exist, but one-way permutations do not exist. Nobody in this area, I think, believes that this is the state of nature, but we are not able to prove it. So what do we know about the existence of one-way functions? If one-way functions exist, then at least NP is not equal to P. So to prove the existence of one-way function, if you have shown that one-way functions exist, you have shown that P is not equal to NP. So you may not want to pick that topic as a master thesis topic. This is probably a little bit difficult. More generally, actually, because P always talks deterministic algorithms, whereas in crypto, we always talk to probabilistic polynomial time algorithms. And in fact, what this really implies is that NP is not equal to a class called BPP, which is roughly P, but where we allow randomness in the we discussed it in this form. It could be that NP is not equal to P, but NP is equal to BPP. Nobody believes it. There are actually strong indications that that's not the case. There are strong indications that BPP is equal to P, but again, we don't know. As in complexity theory, we do know a lot of things, but we often don't know the most important things. So, but it's NP not equal to P is not sufficient to prove that one-way functions exist. For that, you need something else, somewhat stronger. You can modify this assumption that NP is not equal to P to get something that's sufficient and necessary and sufficient to construct one-way functions, but it's not, I don't think it's quite so interesting. But this at least shows that assuming the existence of one-way function is a strong assumption, but also a very reasonable assumption. Many indications are there that one-way functions do exist. and currently think that they might be one-way functions. But to do that, we need a simplifying convention. So far, I always talked about functions f going from 0, 1 star to 0, 1 star. Often we will not, our functions that are candidates are not defined on the complete domain here. They're only defined on a domain D that is a proper subset of this domain here, but still infinitely large. In fact, what we usually have is that for some input length, the function is simply not defined. So it's only defined for certain input length. So example domains are where the function is only defined on bit strings that have an even length and not on odd length, or where the length is n times n plus 1. So it's roughly n for squares. Okay. And here I took these two examples because those are the things that I need for my two candidates. And once you have those things, it's not too difficult to define, then go from these domains, restricted domains to these things. You just pad things and then set it to something that has this format. In particular, what you can do once you have, for example, the domain if f goes from, or let's f bar goes from 0, 1 star to 0, 1 star, you can define a function f, say, which goes from this domain here to 0, 1 star. And what you do, so it's n squared. So then what you can do, you take a pre-image that consists of n bit strings, each of length n. And you map it to f bar of x1 up to f bar of xn. So you apply this function here to the n inputs, or the n part of the input. Okay. And this here has this formula. It's of length n squared. Because if I do it only for n's that are for length n, and then I take n properties. And once you do this, this is actually the way to go from weak one-way functions to strong one-way functions. Because if you want to invert this function here correctly, this f, you have to find the pre-images for all these individual components. So you not, instead of finding one pre-image for f bar to invert f, you have to find n pre-images for f bar. And that gives you the way to go from this part here. You can always, to go from this here. It's hard to invert with non-negligible probability, but then you have to do it n times. And then it's hard to invert almost always, because you will fail with some probability. But to get this here, you are not allowed to fail. But if you give you enough pre-images or enough images, you will fail if you have a significant probability of failing at one position or at least one position. So that's to make this formal is a little bit more difficult, but that's basically that's actually the main idea behind this. Okay. Okay, but mainly we use this simplifying length convention for our candidates that I'll present next. You can make this much more general, and I actually defined it more generally in the lecture notes. But for our candidates, this is enough. So what's our first candidate one-way function? It's multiplication, and I defined it a little bit strange to fit it into the bit string and bit situation, but it's basically multiplication with an important additional ingredient. So the multiplication function is defined on this restricted domain of inputs that have even length. And the reason I do that is for even length inputs, I can partition it into the first half and the second half that have the same length. And then I interpret the first part and the second half as integers via binary representations, including leading zeros. And then what I do is the image is simply I multiply the corresponding integers. And I add 1 to the n. I explained why I add this 1 to the n. It's just a simplifying. It's there to exclude in the inverting game too many easy cases. Okay, so the output is the product of the two components and this 1 to the. And here is that the two components should be of the same length. That's why we restricted to 2 to the. Okay. So now what does that mean to invert this function? Okay. To invert this function means you get just the product of two things. And then you have to find the two components. But because of this 1 to the n, you have to find the components of the same length. Okay. That's why this 1 to the n. So I tell you this here. I want two components in my preimage of length n. Why is that? If I just looked at multiplication and I give you an image of this form, just without this 1 to the n, with significant probability, the image is divisible by 2, or by 3, or by 5, or by 7. And then it would be easy to construct the two products. But they are of different length, so that doesn't count in our inverting game. In the inverting game, given this 1 to the n, you really have to find the product, the factors of the same length. And unfortunately, this product here doesn't tell you what n is, because we may have leading zeros in there. Okay, and you could have could be of length either 2n or 2n plus 1, but because of leading zeros, it could be actually anything. And this thing here tells you, look, please give me things of length. So this here excludes too many easy cases. And the idea here is that, so multiplication is easy. We all know how to do multiplication. At least at some point we learned how to do it. For computers, it's very easy, even large numbers. But factoring is hard. Given product of two large numbers, find the two components, the two factors. At least it's hard if those things are primes, say. Okay? If these things are representations of prime numbers, then we think it's hard to find these things. And that leads us to weak one-way functions. It's only weak because we still have many easy cases. So factoring is not known to be hard. We cannot prove it. In certain cases, factoring is easy, factoring an even number, and this strange definition rules out many of the easy cases. The RSA, which we'll talk about on Thursday, maybe even today, no, probably on Thursday, is something that's based on this candidate one-way function. In fact, we'll see that RSA is based on your one-way permutation a little bit further. So what, okay, so this is multiplication or factoring. Multiply, say, think of two primes, multiplying two large primes is easy. Finding, given the product, finding the two large primes probably is hard. I'll talk about this a little bit in more detail when we talk about digital signatures. Another candidate one-way function, which I think has, but that's probably a little bit of a personal taste, has a better chance of being really hard, being a one-way function, is a so-called subset sum one-way function. The subset subfunctions is defined as follows. If subset, again, it's defined on a restricted domain, and this time it's the restricted domain of things, of bit strings of length n times n plus 1. For all n to 0, 1, and it's defined as follows. Given a bit string of this length, we partition it into n plus 1 bit strings, each of length n. So n plus 1 of length n, we call them x1 through xn and capital J. And x, the xi is also of length n, j is of length n as well. And individual bits of j are denoted by j1 through jn. And again, I identify bit strings and integers via binary representations. And then the image of x1 through xn, comma j is the sum from I to n from ji times xi. The xi's are now integers. The ji's are just bits. So what that means is from the integers x1 through xn, I pick those whose index correspond to index 1 in J. So this J, this thing here, you can identify with a subset of the indices 1 through n, namely those indices where Ji is 1. And you just add up those xi's that are included in the subset corresponding to J. That's why it's called the subset sum function. So we can identify bit strings with integers, but we can also identify bit strings with subsets. And then we'll sum up here a subset. Okay, and this is a function. It's obviously easy to evaluate because all you have to do is add up n integers. We know how to do that. They also do not get too large. Right? Adding two n-bit integers produces, if you're unlucky, an integer with n plus 1 bits, just one more, n plus 2, and so on. So this here is of size at most 2 n bits. A little bit more. But if I just give you this value here, and also this, then you have to, I should also have included this n probably here better. But then you really have to find a subset of size n of the original things that add up to this number, which is the subset sum problem that you talk about in complexity theory. It's one of the first problems that you usually prove that they are NP hard or even NP complete. it's hard. Unfortunately, it's known to be NP hard, but that is not enough to show that this subset sum function is a one-way function, because NP hardness tells you something about worst case assumptions. It says there are things that are hard. It doesn't tell you something about random instances. And our inverting game here talks about random instances. And NP hardness doesn't talk about random instances. It talks about worst case instances. And it's unfortunately also unknown whether hardness on random instances implies hardness on worst case instances. So we don't know whether this is true, but here I think many people are really confident that this is a weak one-way function as defined before. There are many indications that this is really the case. Okay. So these are our candidate one-way functions. We think that, but in any case, we think that they really do exist, these objects. And again, we have lots of flexibility. We just, for our constructions that we discussed in the first lectures in this course, we can work with any one-way function whatsoever, because given any one-way function, we can construct hardcore predicates, we can construct serial random generators, we can construct serial random functions. Okay. So these are some of the candidates that let me briefly tell you these steps that I mentioned in the beginning. And this is what we have also in the lecture notes, the long lecture notes. So if one-way function exists, then hardcore predicates exist. This goes back to Odell Goldreich and Leonid Levin in the mid-1980s. And in fact, they directly basically showed that then PRGs with expansion factor n+1 exist. This is often called the Goldreich-Levin theorem. The existence of hardcore predicates is not shown in the lecture notes. It's a beautiful proof, but I did not include it. But if you really like clever applications of probability theory, this is a really nice example. And then it's also the Goldreich-Levin theorem. Then PRGs with arbitrary polynomial expansion exist. And finally, the thing that I mentioned is that if G is a serial random generator with expansion factor 2n, then actually G is a strong one-way function. So serial random generators are strong one-way functions. This is actually not too difficult to prove. So we cannot get around these one-way functions. Okay. You can also show that if you have a secure symmetric encryption scheme, you have a PRG. You have a serial random generator. So it's not that we just know how to construct these things from one-way functions. They imply also one-way functions. So we cannot get around the existence of one-way functions is just something that we need to have for secure symmetric cryptography to exist. Then we finally have this theorem that if serial random generator exists, then serial random functions exist. This is also a nice construction, very general. It uses a thing called the hybrid argument. It proves that we're going to look at in more detail in other contexts. It's one of the nicest or most important techniques in cryptography. Very much related to game hopping. but slightly proof technique is usually a little bit different, because in a hybrid argument you usually don't use a difference lemma, you do something different. Okay, so to summarize, to get secure symmetric cryptography, we need one-way functions, and once we have one-way functions, we can build the most important primitives in symmetric cryptography. Symmetric cryptography always assuming that participants in a conversation share secret keys. Symmetric encryption schemes are method authentication codes. Let me briefly tell you something about practical constructions as well. In practical constructions, so we use pseudorandom functions to design message authentication codes or encryption schemes. In practice, what we usually use are not pseudorandom functions. We use something that's called pseudorandom permutations. Or you can imagine what pseudorandom permutations are: length preserving, and on each restriction they are permutations on length restriction on the inputs. In particular, symmetric or private key encryption schemes are usually based on pseudorandom permutations in practice. So they are defined similarly to pseudorandom functions, except that they're indistinguishable from random permutations. The security of practical constructions of pseudorandom permutations is only heuristic, which means that no practical attacks are known or were not known for some time. The security often disappears after a few decades for two reasons: additional mathematical insights into the constructions, and the second one is we use certain key length in there, and we do not make them too long for efficiency reasons. And computers get faster, still get a little bit faster, not as faster as they used to. But then you can design special purpose computers so that eventually these things are no longer secure. Examples of practical construction of pseudorandom permutations are the data encryption standard, DES, that was the official standard of the National Institute for Standards and Technology of the United States until 2001, roughly. Triple DES, and the advanced encryption standard. And one warning is, even in the names of these things, the word encryption appears. But these things, you should not be used as standalone encryption schemes, because as such, they are usually not as secure as you would like them to be. They are really pseudorandom permutations, and even in the standardization process, they are described as pseudorandom permutations. That's an important point I want to make. For practical reasons, don't think that AES is an encryption scheme. Although, even if you look at your router at home, it probably says secured by AES, WPA, whatever. But that implies that it's AES, but with additional features built in. For example, AES, pseudorandom permutation, plus randomized counter mode. That gives you something that's really other things include Galois counter mode, things like that. These are then different modes of operations, as I call it, and then they lead to these. Really lead to the encryption schemes, the symmetric key or private key encryption schemes. Okay, that's all I wanted to say about these constructions. As I mentioned, if you are interested in the details, look into the lecture notes. I provide many details there. If you are really interested in the fine-grained details, look into that Goldreich book. He provides all the details. But also in the book by Katz-Lindell, you find all the details of these constructions. Okay, and with this, we are going to leave the area of symmetric or private key encryption scheme, or private key cryptography. So private key or symmetric cryptography always assumes that we have these shared secret keys for encryption schemes or for message authentication schemes. We saw that. We did not talk so far about how we can actually get those shared secret keys. And the area that we are going to look at next, namely public key, asymmetric cryptography, gets around this problem of shared secret keys. So it constructs things, primitives that also achieve confidentiality, authenticity, and many other features without assuming that shared secret keys exist. In practice, in some cases, like in encryption schemes, for example, it's not just a way to get around shared secret keys, it's also a way to achieve shared secret keys. And the next things that we are going to do is we are looking at digital signatures. This is an extension of message authentication codes to the domain of asymmetric cryptography, which has nice additional features that you cannot achieve with message authentication codes. And we also look at asymmetric or public key encryption schemes. In both cases, we try to construct these things from general assumptions. And in the case of digital signature schemes, we'll see that, again, one-way functions are good enough to get digital signature schemes. For asymmetric encryption schemes, we are not able to prove that. We use different objects, namely trapdoor permutation. And it's sort of unlikely that pseudorandom, that one-way functions are good enough to get public key encryption schemes. I will come back to this point later in the course, and then I will stress again that many people think, also practitioners, that digital signature schemes and public key encryption schemes are almost the same. That's not true. That's really far from the truth. But those things I'll start talking about on Thursday, because I don't think it makes much sense to start with introduction to digital signature schemes for 30 minutes or so. And then I think we'll just stop here for today and continue then on Thursday with digital signatures and public key encryption schemes. Okay, thank you.